Welcome to the deep dive. Today we're digging into a really crucial moment in physics, a time when conventional wisdom was just completely overturned.
That's right. We're looking at how order is even possible in two dimensions when all the arguments said it shouldn't be.
And this all comes down to the Berezinskii-Kosterlitz-Thouless theory, or just BKT.
Exactly. Our mission today is to unpack how a pretty abstract idea, topology, managed to solve a very concrete physical puzzle. It's all about defects.
Okay, so let's set up that puzzle. The central paradox. The established thinking from guys like Peierls and Merman was pretty clear, right?
Oh, it was very clear. The argument was that in a 2D system, you simply can't have true long-range order at any finite temperature.
Meaning no perfect crystals, no superfluids, nothing like that.
Exactly. The problem is low energy fluctuations. I mean, think of it like a huge, thin sheet of rubber. Any little wiggle or stretch just grows and grows until any sense of order across the whole sheet is just gone.
So the atoms can't stay in formation.
They can't. So no ordered state, which means no phase transition to an ordered state, seemed pretty open and shut.
But then the experiments started saying something different.
That's where it got interesting. The counter evidence was really compelling. People were doing experiments on these ultra-thin films of helium-4.
And what did they see?
They saw a clear, really abrupt change as they lowered the temperature. It was snapping into some kind of new ordered phase.
Which theory said was impossible.
Completely impossible. So the picture had to be missing something.
So if it's not traditional long-range order that's being destroyed by all those wiggles, what is it?
It's a much more subtle kind of order. It's called topological order, and it's protected in a different way. It's not about resisting those small fluctuations.
Okay.
It's about making it really, really hard, energetically expensive to create a specific kind of disruption, a topological defect.
And for a superfluid film, those defects are vortices, little whirlpools.
Exactly. And here's the beautiful part. The way these vortices interact with each other. It follows a logarithmic energy law, and that makes the system mathematically identical to something completely different.
Which is?
A neutral plasma of Coulomb charges in 2D.
Wait, a plasma? So you're saying these little swirls in helium are behaving like positive and negative electric charges?
That's the analogy, and it explains everything.
How so?
Well, at low temperatures, these charges, the vortices, are all tightly bound together, a positive with a negative.
Like dipoles. So they cancel each other out.
They're neutral pairs, yeah. The system is calm, but as you raise the temperature, you reach a critical point, the BKT transition. And at that point, the energy cost to create a single isolated vortex just vanishes.
So the pairs can break apart.
They unbind. Suddenly you have all these free positive and negative charges roaming around, and that's what destroys the superfluidity. The subtle topological order is gone.
So this analogy, it's not just a nice picture. It must make some kind of testable prediction.
It makes an exact prediction, a really inescapable one. It predicts a universal specific value for the jump in the superfluid density right at that critical temperature.
A hard number that you can go and measure in the lab.
The hard number. And that's what Bishop and Reppe did in 1978. They went and measured it.
And the result?
It was a stunning confirmation. The experimental data from several different groups all fell perfectly on the theoretical line predicted by BKT.
Wow.
And here's the kicker. Some of that data had been plotted before the experimentalists even knew the exact theoretical prediction. The theory just fit the existing observations perfectly.
That's incredible. So did this idea of defects unbinding get applied to other things? What about, say, 2D melting?
Absolutely. The Kosterlitz-Thouless idea, with some more work from Halperin and Nelson, showed that 2D melting isn't a simple one-step process.
It's not just solid to liquid.
No, it's a two-stage process. First, one type of defect, dislocations, unbinds, and you get this strange intermediate phase, a hexatic fluid. Then another type unbinds, and you get a true liquid.
So to wrap this up, the big lesson from BKT is that order can exist in 2D. It's protected by topology, not by rigidity. And it survives until you hit the system with enough energy to unbind these high-energy defects.
That's the core takeaway. It completely changed our understanding of phase transitions, and it leaves you, the listener, with a fascinating thought to take away. Topology, this really abstract branch of math about shapes and holes, provided the exact framework needed to explain something very real and measurable, like a thin film of helium. So the question to mull over is this. What other physical phenomena are just sitting there waiting for us to figure out what their underlying topological defects are?